Hey there, welcome to a video discussing section 7.2 on the indefinite integral and anti-differentiation using substitution. So let's first define an indefinite integral, how it compares to a definite integral, which I actually have as a question on the Google form that goes with this video. So the family of all antiderivatives of a function is called the indefinite integral of f with respect to x. So what this means is that you're going to have a plus c at the end. And also, the answer is going to be an expression. And yes, it does represent the family of all antiderivatives of some function. So, for example, what if I take the antiderivative or the indefinite integral of x squared dx? Then the answer would be x3 over 3 plus c. So that's what's meant by the family of all antiderivatives of the function x squared. So it's plus c at the end, and it's an expression. Now, a definite integral would have been this. Say I go from 0 to 2 of x squared dx. So a definite integral is one where you get a number and it represents the area between the curve and the x-axis. So in this case, x cubed over 3 from 0 to 2. You plug in 2, plug in 0, take the difference, you get 8/3 is your answer. So that's the difference between an indefinite and indefinite integral. We'll work on indefinite integrals in this section here. In capital F, remember, we call that the antiderivative. And so if you do the derivative of the antiderivative, it gets you back to the f of x, which is part of the fundamental theorem of calculus. Or the integral of the f of x equals capital F of x, where capital F of x is the antiderivative. And we tend to write indefinite integrals just like this. Oh, my stylus is no longer working. I need a new one. Put that back in. Yeah, so we tend to write indefinite integrals like this without limits of integration. So no limits of integration. That's another difference between that and a definite integral. We don't have limits of integration because we just want an expression as our answer. So in this case here, you're asked to find the indefinite integral of e3x dx. Well, that's just going to be e3x over 3 plus c. A little bit weird why I did it that way. Why does it come out that way? So some people might think it would be this. But that's not true. Because if I took the derivative of this, of that using chain rule, I have 3 e3x, then times another 3, and then of course the root of c is 0, then you have 9 e3x. That's a problem. The reason why you want to divide by 3 is that if I take the derivative of that and do my chain rule correctly, so derivative e3x is e3x, derivative e of whatever is always e whatever, but in times 3 plus 0, and those 3's cancel. So in essence, what we're doing is we're actually dividing by its coefficient. We're going to talk about that in a little bit, why that's important. But by intuition, hopefully you can see why it's e3x over 3 plus c, because after you do the antiderivative, you do the derivative of e3x3, you need to get back to e3x. Other things to take note of. This one's pretty easy. That's just x cubed plus c. But remember, this is a definite integral. I just described that difference to you. That's still x cubed. You don't need to put the plus c because it's a definite integral. 1, 2, and then you work it out, you get 8 minus 1, you get 7. So that gives us an answer. And here, notice that these are all the same thing. Who cares if you do a different letter like X or T or R, S, they're all the same thing. They all represent area accumulation. So the letter just doesn't matter. You just work it out. It's the same thing as up above. All these are going to equal 7. So the letter that you see here doesn't really matter. Actually, sorry. They're going to equal not 7. That's when you had 2 as the upper limit. My bad. You just had X here. You know, they're all just, if you were to work it out, they all get you X cubed minus 1, I believe. Yeah. Yeah, because you're just integrating each of these. Like, for example, that'd be t3 over 3. You plug in 1 and x. Actually, I lied. It's 3t3 over 3. Let me backtrack a little bit. Sorry about this. If I were to work that out, the antiderivative 3t squared is 3t cubed over 3. My bad. From 1 to x. Remember, you add 1 to the exponent, divide by the new exponent. Those cancel. Then you plug in x. You get x cubed minus 1. So all these equal still x cubed minus 1. And they represent area accumulation as a function of x. Okay, sorry about for botching that. Properties. If you have a constant, feel free to pull a constant to the left and then just focus on the rest of the integral. You totally can do that, k times that integral. If you're adding two different functions, feel free to break them up like this. Integral of f of x plus integral of g of x, so you can do them independently. And plus or minus, so it doesn't matter whether it's plus or minus. Other kind of useful rules to know regarding integrals that we can just pull out of our back pocket from time to time. This one here is going to be just, well, first of all, if you take the derivative of this guy right here, doing a product rule, in case you guys forgot, if you do a product rule, it's going to be 1 times ln x times, plus x times 1 over x, and then minus 1 here. So you get ln x plus 1 minus 1, those cancel. So you get ln x. So what this tells us, the conclusion, is that the integral of natural log of x dx, put this in parentheses, equals 1 over x, and plus c, of course. Don't forget about the plus c. Oh, another thing too that's, oh, wait 1 sec. Goodness. Okay, just made another error. My apologies. What I meant to say was the conclusion is that the integral of ln x dx equals that chunk right there, x ln x minus x plus c. Sorry about that. So that's the integral of ln x. Is that the integral of 1 over x dx, that's ln x. That's what I meant to say. But I just got confused. So my apologies there for that one. Now here, what if you're given y equals natural log of x? We know the derivative is 1 over x. But because this represents an absolute value, what if I do a piecewise function? You can have natural log of x if x is greater than 0. Or actually, yes. If x equals 0, obviously it does not exist, because you can't log 0. That does not exist. Or you can do natural log and then negative x if x is less than 0. So negative x right there. So then if you were to do the derivative of this, dy over dx is definitely 1 over x, or it'd be 1 over negative x, but then you got to do a chain rule, so times -1, so you still get back to 1 over x anyway. So what this tells us is that when you do the derivative, when you do the integral of 1 over x, you simply get ln x plus c. And the assumption is that your x is going to be positive or greater than 0. Or you could just do this. The integral of 1 over x dx is natural log absolute of x, then plus c. And again, up here, the integral, which I botched, my apologies, of natural log of x dx was x times natural log of x minus x. So that's what we're seeing there. Okay, now let's keep moving. Power rules, I've mentioned before. You add 1 to the exponent, divide by a new exponent, plus c, provided the n does not equal 1. But when you have 1 over x, you can't do that rule, so there's just going to be natural log of x plus c. And again, the assumption is that x is positive, or we put absolute value around it. Here, remember, these are very similar to what we saw last semester with these rules here, where we had derivatives and we could go in this direction from left to right. Derivative sign is cosine, derivative cosine is negative sign. So now you go in the opposite direction here. Now you're going to say this is going to be sine x plus c, where this is going to be negative cos x plus c. Over here, this will be tan x plus c. This will be negative cotan x plus c. Here, this would be secant x plus c. And negative cosecant x plus c. So this is like your cheat sheet. This is like your best friend here. For here, that's inverse sine of x plus c. Inverse tan of x plus c. And inverse secant of x plus c. For exponential and log formulas, that's straight up just e to the x plus c. Now we've seen this already. X ln x minus x plus c. A to the x times natural log of a plus c. Actually, you got to divide by natural log of a because it's the opposite of derivatives. Because if you were to take a derivative of this, you would get back to a at x. And here it would be, you kind of think of this as using the change of base formula. So ln x over ln a dx, and ln a is a concept which could be pulled out. So here I'm using the change of base formula, just so you know, for logs. And then you can pull it out, so you have ln x dx. So it's 1 over ln a. And remember, we already talked about the antiderivative of ln x being x ln x minus x, and then plus c at the end. And you don't have to have the c inside because c divided by ln a is still a constant. And our constant is a very general way of writing it. So you don't have to have the plus c inside the parentheses there. So let's work these out. Here you have to find the antiderivative f of x. F of x is this right here. So that's going to be x cubed over 3 plus x plus c. That's part A. So that should be pretty easy. What if you replace the x with a u? So f of u is now u squared plus 1. Fine. That's what I'm integrating. I'm integrating u squared plus 1 du. Well, it's u cubed over 3 plus u plus c. Great. But this next one's going to be a little bit, and it is, you said to do in terms of x. So actually, now I got to replace the u with x cubed. So it actually becomes x to the 9th power over 3 plus x cubed plus c. Because I'm replacing the, yeah, so I replaced x with u, had u squared plus 1, I worked it out, but then I had to replace the u with x cubed. Now this is interesting. That's an interesting one. You're integrating f of u, which again is u squared plus 1, but then dx. So those are not the same. So what you need to do then is then replace the u right off the bat with x cubed. It becomes x to the 6th power plus 1, and then you work it out. You get x to the 7 over 7 plus x plus c. So the moral of the story, I'll put it right here as a text box in red. You must carefully consider the variable of your integrand. That's what you're integrating. And the differential. The differential is like, dx, du, etc. And let me move that so you can see it a little better. So you must carefully consider that. So A was easy. We knew f(x) is x squared plus 1. With respect to x, you work it out. You get x cubed over x plus c. Here at f of u du, that's fine. Replace x with u. So you have u squared plus 1. And doing it now with u, so great. U cubed over 3 plus u plus c. And then you put the u equals x cubed into your final answer. You got x9 over 3 plus x cubed plus c. Whereas here is f of u dx. And that's where we're gonna see that kind of stuff more frequently, like what we see for part C. So that's gonna be on the next page. So differentials. dx is called a differential. And here we have u equaling u of x. It's a function, u is a function of x. And we can define the differential du by the following, which kind of makes sense because the dx is just cancel here, right? But essentially what you're doing is you're taking the derivative of u with respect to x. And it turns out to be very useful. So let's take a look at example 3 here. Then I'll do examples 4, 5, and end the video. So this is called substitution. We saw this in the 7.1 notes. Remember we did this by inspection. Let me pull it up really quickly here. Lecture notes 7.1 filled out. Yeah, we saw it over here. We kind of just did it by inspection. We kind of realized, well, maybe it's just e7x squared because the derivative of that gets us 14x e7x squared. But now I'm going to give you a more mechanical approach to this. What if you let u equal 7x squared? Fine. You have 14x times e to the u power dx. The problem is that you got u's and x's, so it's a little confusing. Let me actually rearrange this just a tad. You have eu times 14x times dx. Now, here's the thing. If u equals 7x squared, what's the derivative of u with respect to x? Well, it's going to be 14x, of course. And what if I multiply both sides by dx? I get this. So all of this right here equals du. So now I can rewrite as eu du, take my integral, or antiderivative, which is eu plus c, and then, because u is 7x squared, bring it back into the mix, and now I got my answer. So that's called u sub. This is right here is called u sub. You're making up a letter called u, and you're letting u equal some portion of the integrand, and then you're taking a derivative of u with respect to x, as I did over here, and then doing some rearranging with the algebra by moving dx to the other side, and then substituting that in to my integral expression. So I just get everything in terms of u, and then I work out the integration. Then whatever u equaled, bring it back into the fold. So that's kind of what's going on there. Let's look at example 4, and I'll explain what's going on in that box there. So what if you let u equal 1 minus 2x to the 5th power? Okay, so my integral will be this, 7x4 times root u times dx. And let me rearrange it like this. I'll make it u to the 1/2 power, by the way, times 7x4 times dx. Now, if u equals 1 minus 2x5, what's du dx? The derivative of u with respect to x. What's that going to be? If I do d dx both sides as an operator, it's going to be negative 10x4, right? Negative 10x4. If you do a little rearranging, you can move the dx to the other side and maybe move the negative 10 by the du. So you get this x4 dx. So now you can do is the x4 dx over here is the same thing as du over negative 10. So now we can rewrite their integral in this fashion. The integral of u1/2 times 7 times du over -10. And now that's what's meant by this dialog box. We can fix a missing constant. So don't worry about like you got -10 as a constant. You can always move to the other side. So you can treat it like a multiple, but variables you can't quite do that because you got to substitute for x4 and dx simultaneously. But who cares about the 7 here? It all takes care of itself because now I could push the constant off to the side as we saw earlier on with constant multiples. Here we go u1/2 du. And now I'm going to work this out. That's going to be u to 3/2 over 3/2. Remember, add 1 to x minus 5 and the x minus a power term. You get -7/10 and plus c. The 3/2 you can flip, so it becomes -7/10 times 2/3 times u 3/2 plus c. These cancel. So you get -7 over 15 times u 3/2 plus c. And then you could bring the whatever u was. U was 1 minus 2x to the 5th power. So you have -7/15 1 minus 2x to the 5th power raised to the 3/2 power plus c. And that is your final answer. Now, how do you know you did this right? Take the derivative. If you take the derivative carefully, -7/10, move the 3/2 to the front, so you're using chain rule. So that will become -21 over 20, I believe. And you have 1 minus 2x5, drop the exponent by 1, so it becomes 1/2. And you got to do a chain rule, so you got to multiply by negative 10x. And when you clean it all up, negative 10x to the 4th power, my bad. When you clean it all up, let's actually make sure I've done this. Oh, oops, that was 15, my bad. That's a 15, so that should be a 30. So yeah, now I feel better about this because then I get 210 over 30, which is 7. And I can, of course, have the x4 right here as well. So it all works itself out nicely. Okay, let's try one more. Now, one rule that you want to do when you do u sub, you tend to want to let u equal the expression that's a bigger exponent. And then you're going to have to get good with identifying what u has to equal. So let's say u equals y6 plus 5y squared minus 3. So du dy, remember just in terms of y now, not x, is 6y5. These are dummy variables, doesn't really matter, plus 5. Oh, sorry, that's y squared. So plus 10y, my bad. Let me refix that. Now, notice this 3y5 plus 5y. You could deliberately pull out a 2 from here. You have du dy, and then you can actually move the dy over to the side. So du equals that, and then divide by 2. So you have 3y5 plus 10y times dy. And so all this can be substituted. So now you have the integral of 10. I'm going to push a 10 off to the left here, of u to the 7 power times du over 2. Or it becomes 5 integral u7 du. Once you have that in play, then it becomes 5 times u to the 8th power 8 plus c. And then remember, u was 5y6 plus 5y, y6 plus 5y squared minus 3. So it's 5/8 of y6 plus 5y squared minus 3 raised to the 8th power plus c. You can take a derivative of that if you like to see if you did it correctly, but we'll just trust the process here. So we'll have a chance to kind of let that simmer overnight. And we'll do some more stuff tomorrow with this, some more complex problems, pages 4, 5, and 6. We'll do that for the first hour, then we'll do some test review the second half of our next class. All right, see you guys later.